Okay, welcome everyone to the second session. Thanks for joining. So this talk, we started this on Tuesday. We initially went through, just to recollect what we did on Tuesday. So we went through a little bit of a biographical sketch and my experience going through first at CEG itself, and then through my master's and PhD programs, and also working on a few industry internships and my academic and industry career since then. And then we started talking about the university which I'm a part of, the departments and the centers that I'm involved with. And then we started talking about the power system as a whole and how the power generation, consumption, distribution, all of these aspects are being affected by influx of power electronics, and how we like to call power electronics an enabling technology because it enables progress in several other applications, right? So we talked about computing applications, we talked about transportation applications, power generation and energy storage, and specialized applications like for electric aircraft and ship. And we also saw how a traditional grid, which used to be fairly unidirectional, you used to generate power at a large power station, and then you used the transmission network to send power towards the places of consumption, which we call load centers. And the load centers themselves could be commercial, industrial, or residential. And then the distribution network carries the power down to the residential, commercial / industrial loads. And we saw how this very simple architecture has been changed into something a lot more chaotic and a lot more complex. You can see here on the left the traditional power generation that comes from nuclear, coal, gas-fired, etc., is only one of several sources, right? So we have wind power, we have solar, we have even things like pumped hydro to manage energy and power flow in the system. And then you have solutions like microgrids that address generation and consumption at the local level instead of being tied to a centralized grid at all times. And on the consumption side, also, you've got residential applications, industrial and commercial applications, and then you've got transportation applications. You've got electric trains, buses, vehicles, personal vehicles, public transit vehicles, going up to ships and aircraft and stuff like that, right? So it's a much more complex world, and it is a much more what is required now is a much more sophisticated way of addressing power flows and energy management, and that is being done by power electronics, right? So if you look at this picture and try to locate where the power electronics are, certainly in traditional power stations to manage certain operations of the generators. You've got wind, which is heavily power electronics enabled, solar power electronics enabled. You've got HVDC systems, which is power electronics enabled, power flow, UPFCs, eStatComs, off-grid energy storage, MVDC, SSD, solid-state transformer, StatCom or static work compensators, And then you've got chargers, right? Chargers and power delivery mechanisms to transportation systems. And then on the consumption side, also you've got MVDC, which is medium voltage DC systems. And then on the load side, you've got, of course, your residential applications, commercial applications like motor drives, etc. All of this is enabled by power electronics. So it's a much more integral part of today's power generation, transmission, and consumption, right? So we jumped into, I think this point is where we stopped at the last meeting. So one way to understand this a little bit better is, this picture is very chaotic, right? It's a massive, massively high-level view of what is going on in the power grid today. So it'll be helpful to split it into a couple of different areas, right? So we can talk about generation, and then we can talk about consumption or use patterns, right? So when it comes to generation, of course, there are several different ways that power electronics enables power generation. We saw solar, wind, et cetera, et cetera. So instead of going through all of it, I thought we could talk about one concept called virtual power plants, right? We all know what a power plant is, what it does to generate power and transmit power to the load centers where the power is being consumed. Now, it will be helpful for us to understand first how the power system operates. How do we generate power that we need, and then we consume that power, right? So the thing about power grids is, and this is somewhat obvious to most of us or all of us, is that power that is generated in the power stations or at the power stations now is being consumed almost instantaneously, right? So there is no, and you can talk about power or energy storage devices like batteries, etc. But other than that, most of the power that is generated at power stations are being consumed almost instantaneously, right? So the transfer of power happens almost at the speed of light, very close to the speed of light. So how do we know that in a city like Chennai, how much power is needed at every instance of the day, right? So we need to know how much power is required at every instance of the day, and then we need to make sure that the power stations generate that much power, because if they don't do that, we will have instabilities, right? So if the consumption is more than what is being generated, obviously the quality of the power that you receive is going to drop. And of course, in more extreme cases, we all know what happens if the generation is too small. You start having blackouts and brownouts and things like that. So how do we know in the operation of the power grid, how do we know that we need to generate so much power at the power station, right? So the way it is done is there are a few different systems when it comes to the power grid. One is a so-called vertically integrated system in which the generation, the transmission, the distribution, all of that, and the operation of the grid itself, it happens, it is done by the same entity, right? In a lot of states in India, it is a vertically integrated system, and we have basically government-run power grids. And of course, we do have some private entities involved in generation, transmission, distribution, but largely speaking, the power grid itself is a vertically integrated system in a lot of states in India, and that is true for many countries. There is also another system which is not so vertically integrated, where you have entities involved in generation, entities involved in transmission and distribution, the infrastructure, and then you have utilities involved in the consumption of power at the load centers, right? So one way to, almost all of these systems, you need to do a couple of things for the whole system to operate smoothly. The first is forecasting and analytics and economic dispatch, right? So what does that mean? Of course, you have policy mandates and things like that feeding into how the power grid is designed and operated. You've probably been seeing in the news, governments around the world, they say, well, by the year 2030 or 2040, I would like to have all of my generation coming from renewable sources, right? Now, that is not driven by any market demand, that is driven as a policy initiative from the government, right? So that feeds into the system as well. But when it comes to day-to-day operations, the first step that happens is forecasting and analytics. So what you do is you using historical data and using machine learning principles, one could predict the load and resource forecast for a future time period. Typically, it is done, at least in the US, it is typically done over a 24-hour period. So today is Thursday. So what they'll do is tomorrow by this time, how much power is going to be required by my area of operation, right? So a city or a region, how much power is it going to consume tomorrow this time, right? So they do that using algorithms which use historical data. So tomorrow is a Friday. Tomorrow is a Friday in the month of April. So they have all this information available to them, historical data. So using all of that, and are there any special events happening, right? So maybe there is a festival and everybody's decorating their houses with lights, right? So then there's going to be slightly increased power consumption. So they have all of this information and they feed it all into their algorithm, and it predicts how much power will be needed tomorrow this time, right? So that's the so-called 24-hour forecast. Then there is an economic dispatch, right? And this happens more so in the non-vertically integrated systems or deregulated systems, right? Where they would invite people to, when I say people, invite power generation entities to say, yes, I can provide that much power 24 hours from now, or I can only provide a smaller amount, right? So that kind of a negotiation happens. So that is the economic dispatch. When all of that is done, what's called a dispatch schedule is created, in which, based on a number of different factors. So there are large power stations and small power stations. So depending on the rating of the power station and depending on how much power is available at that point in time. For example, solar, we have solar here and we have wind here. So that is the resource forecast side of things, right? How much sun can we expect tomorrow this time, right? How much wind can we expect tomorrow this time, right? And that is accomplished by taking in weather data. Very accurate weather forecasting can be performed. So all of that tells us, or that tells the grid operator, how much load is going to be consumed at a future time period, and how much resources are available at that same future time period. And then, like I said, depending on the ratings of the power systems or power plants, a dispatch schedule is created whereby they say, well, at this time tomorrow, power station 1 generate this much, power station 2 generate this much. And this is, like I said, it's a negotiated agreement that happens between generators and grid operators, right? So that is what this picture is is trying to capture. So there are load centers here. You can see the picture of a town here, and then you have generating happening from distributed energy resources. And in the case of a typical or more traditional power grid, you also have your traditional large power stations also, right? So that's how a power plant operates. But a virtual power plant, on the other hand, what it does is it integrates or it groups loads and generation that exist in a region. You can see this dotted line here. So it would be like, if I can use the Chennai example, Chennai obviously is a city where a lot of power consumption happens, but surrounding the city there may be some power plants, or there may be solar power generated in Chennai to some extent, right? So all of that goes into the load demand at a future time, the generation capacity at a future time. All of that can go into the power and energy management algorithm of a virtual power plant, right? So once that happens, like I said, at the future time, the stations generate that much power, and then we are all fully balanced. And like I said, if there is no balance between the generation and the demand, you're going to have an unstable condition. Best case scenario, the quality of the power goes down, and worst case scenario, you could have a blackout, right? So if I zoom into it further, you can see where all the power electronics and all the algorithms exist. So this just zooms into the two different areas. One is the forecast and analytics part of a virtual power plant, where you have accurate weather forecasts. So we have temperature at a certain point of the day, solar insolation. This just is a word that tells us, is a quantity that tells us how much power from the sun will be available, right? And then you have wind speed, right? So using these, one could predict, the load forecast. For example, if you have a very high temperature, that will result in a higher power consumption, right? Because you have the fans and air conditioners and refrigerators, everything, they have to work harder because the temperature is high, right? So using the weather forecast and the historical databases, you can predict how much load is going to be consumed at a certain time of the day, let's say tomorrow or the day after, etc. So that is fed into the dispatch schedule. The same goes for solar PV and wind turbine production or power generation, right? So once again, you have historical data available for you, and you can use that information to predict how much power can be generated by your solar PV stations and your wind turbine stations, right? And then you create this dispatch. By the way, like I said, this dispatch, it might have an economic dispatch component or not, depending on how vertically integrated a system is. So if there is no vertical integration, there are several entities involved in the generation, transmission, and distribution of power. These different entities are, they need to enter into these negotiated contracts with the grid operator based on how much they will get paid for a certain number of megawatt hours, etc. Right? So all of that is fed into a central dispatch controller, and this dispatch in the vertical in the virtual power plant environment, it can be dispatched to the different assets that exist in the field, which are, you have a solar PV here, a wind PV here, a wind plus battery here, and then you have a solar PV again here. And then we have battery energy storage systems as well. So what this dispatch tells these the controllers of these various generation devices, if you will, is, hey, tomorrow by this time, you need to create so much power. And we know that that much power is possible because we have made that prediction using weather forecast and load forecast information. Right. One other thing that we have here is this ADR controller. What this ADR is called an automated demand response system. What it is it is able to regulate or turn off, if you will, power that is being consumed at a certain location. And typically, a large industrial customer or a large center like this public facility. So the reason why this is done is because if you estimate an increase in power consumption in your city, right? This city, it requires a sudden increase in power that is required. You can meet that by using two methods, right? One method obviously is you can increase generation here, or you can see this is connected to the larger power grid, right? So you can increase power generation at one of your large power stations, or you can increase power generation from any of these guys, right? But what an ADR does, the second method, you can meet that same increase in demand from the city, is you can reduce the demand at a large factory or a public facility. Now, if you have a huge, like a mall, like a huge mall, for example, is fully air conditioned, and you know that there is going to be a sudden increase in demand at a hospital, right? Obviously, you need to meet the demand at the hospital because it's a critical facility. So what you can do is, if the right ADR system is available, you can maybe decrease the power consumed by the air conditioner at the huge mall, right? Because the air conditioner, you can reduce the power consumption, or you can turn it off for 10 minutes, 15 minutes. It's a thermal system, so it's not going to fluctuate very quickly, right? So such dynamic increase in demand can be met by using automated demand response systems, right? So you're responding to the increase in demand, and that is the so-called DR, demand response, right? So that is how, this is a very high-level description of what a virtual power plant could look like. Now, like I said, you have power electronics here, power electronics here, power electronics here, power electronics here, and also here. So you can see how this is quickly becoming an enabling technology for all of these systems, right? So at this point, I would like to pause and see if there are any questions at this point. Any questions from the students who are on the call, or maybe Kumaraguru, you have some questions?
Yeah, I mean, I started reading about this in context of the electric vehicles mostly. The question I have is like, it looks like everything is centralized control, or is it more decentralized control? Is how like a hospital A versus hospital B would be prioritized in real systems, right? So is there like standards or something, or how does that work?
No, there's no standard per se, but there are practices. Even today, this is a virtual power plant is a not just a concept. There are solutions available for regions and jurisdictions and grid operators to install and operate. But even in today's grid, like a traditional grid, loads do have some categorization, and high prioritized loads are identified, right? And typically what happens is that such prioritized loads, they have some kind of a UPS system involved. installed. Could be just a generation, like a diesel powered genset or something like that, right? So the grid operators, they know where the critical loads are. They know, they do take into account when they design the distribution system. And the distribution system itself contains fallback options, right? So if you look at this, if I can use this diagram as an example, so let's say you have a critical load somewhere here, and there is a failure upstream, whereby a tree has fallen on a power line or something, right? So in such situation, or maybe they have to do some maintenance here, right? In such situations, they operate these devices called switches and reclosers, right? And there is redundancy built into the system. So this same hospital has another line going back to the main feeder, right? But that is kept normally disconnected, right? But during the abnormal operating conditions, they do connect that normally disconnected line so that the critical loads continue to receive power, right? So these things are taken into account already. But in a future system, right, so that all these can become part of the decision-making process. So what can I prioritize? Like you said, you have hospitals, prioritize them over, let's say, a commercial place of business, right? So that can and will be a part of the decision-making algorithm, I think.
Yeah, it's very interesting because we are also entering into some dynamic pricing for different applications. So yeah, it's interesting how these all will work out.
Yeah, and you talked about, you mentioned electric vehicles, and electric vehicles, I think the prevailing opinion is, at least in certain power grids, they can be part of this ADR, right? Because it has to be in some level, because if you can imagine a city like Chennai, right? There are so many vehicles in the city. Imagine they all become electric vehicles, and they all, people go back home and they charge their vehicles at the same time, and that's going to result in a massive load on the power grid, and that is probably not very sustainable. So there you could envision a program in which the device or the vehicle can communicate. For example, 8 p.m. to 10 p.m., they can charge vehicles in a certain part of the city, and then 10 p.m. to 12 midnight, they charge vehicles at a different part of the city, etc. And they can control and regulate when the electric vehicles in different parts of the city are being charged. Because if people charge them all at the same time, which is very, very possible, because, or even probable, I would say, because people go home in the evening and they connect their vehicles to be charged. So that can become a part of the ADR systems in the near future. There could be mandated requirements, like in some jurisdictions, the governments could require that, because they don't want the grid to be taxed too much and the grid starts to fail. But in certain other jurisdictions, it could be an incentive program, right? So what the power grid operator could say is, hey, owner of electric vehicle, participate in my program, where I decide when to charge your vehicle and when to not charge it, and I'll give you a little bit of a discount in the electricity prices, right? So that could be an incentivized program as well. So there are a couple of different options there.
We were really exploring those areas. It's very interesting.
Yeah, of course. Any questions from the students so far? Samreen and Jessima. I know I'm putting you on the spot. Okay, so jumping ahead, so that's virtual power plant. So once again, all of this involves power electronics in some way, and virtual power plants are one way to look at the power grid of the future with a lot of DERs, we call them. DERs are distributed energy resources, solar, wind, battery energy storage solutions, even electric vehicles, as we've been talking about, right? So that's about the power generation side. And this is just just a cartoon to make a point that it is not just about power generation, transmission, and consumption. It is also about the quality and the reliability and the resiliency of power systems, right? Reliability and resiliency, they are similar sounding words. Their meanings are also very close to each other, but if you look very closely, reliability is a highly reliable system. It just doesn't fail, right? That's the meaning of the term reliability. But a highly resilient system, what it does is you could bounce back. If a failure does happen, you bounce back to provide power service to the end users very quickly, right? So that's the difference between resiliency and reliability. A highly reliable system could be very poor when it comes to resiliency, and at the same time, a very resilient system which bounces back quickly could also be poor when it comes to reliability, right? So these are two different concepts. So the reason this is here is to show how using these DERs, using these different types of generation, transmission, distribution, and energy storage assets enabled by power electronics, one could improve, first of all, the reliability of the system and also the resiliency of the system, right? How do we improve reliability? Because just imagine a world in which these distributed energy resources did not exist. That would just look like this picture, right? So if you load the system more and more, right, your generation, let's say, it has not increased in some time, but your loads keep on increasing. People buy more devices, they have electric vehicles like we talked about, and then there are more people in a particular city, let's say. So the consumption keeps on increasing, but the increase in generation has not really kept up. So that stresses the system more. It could lead to more failures. So that results in poor reliability for the entire system. But if you have, let's say, distributed energy resources that are generating some of the power at the point of consumption, like for example, your industrial load, it could have some solar on the roof, or all your houses, let's say in a certain city, they have solar power production. Same thing for offices, right? Parking lots. Let's say we have a lot of power generation happening there. So the power that is being consumed at these so-called load centers, at least part of it is being generated right there, which means that the stress that the transmission and distribution system experiences, it goes down, right? And that leads to increased reliability. Resiliency also increases because if you have a failure, if you do have a failure in the transmission system or the distribution system due to whatever reason, it could be weather related, it could be it could just be a catastrophic failure in a certain power station. So if you have, once again, distributed energy resources, solar, battery energy storage, small wind, etc., one could just meet local demands for power from generation that is happening locally, right? So you can quickly bounce back when it comes to providing power to the end users right after a failure in the transmission system or the generating plants, right? So you can see how both resiliency and reliability can be improved by using distributed energy resources that are enabled by power electronics, right? So there's a lot of research activity in this space all over the world, really. So if the students are interested in, and you don't have to be a power engineer to engage in this type of research. And as Kumaraguru was pointing out, some of his past efforts, they've looked into these kinds of things, even though he's not a power engineer. So I'd encourage the students to look into such topics. Okay. Any questions on this before we jump? Okay, very good. So far, we talked a lot about power generation. So now we can look at some of the consumption-related aspects. And this little picture is from Texas Instruments. So this talks about power management for various different loads, like for example, and there are different aspects to improving efficiency and improving power and energy management at the consumption side, right? So that is what is brought out in this slide. So you have power management and you have energy management, right? So there are different loads in your house. If you look around the house, you have your television, you have your washing machine, your fridge, your maybe an electric cooker, right? And you have things like cell phones and computers. All of those devices need power, and the power flow to those devices and inside those devices, all of that needs to be managed, right? Either by the end user themselves or the manufacturer of the devices themselves, right? And so this is what this section is all about. This section of the presentation is all about. So you have, if I can jump ahead, we're going to look at different applications and perhaps from this material, some of the students will understand there is power electronics in these various different places, and this is something maybe they were not aware of before, right? So the first application that we are looking at is lighting, right? So lighting traditionally involved either a fluorescent lamp or an incandescent bulb, right? So that's what lighting was. You can also think about halogen lamps and solutions like that for street lighting, right? As you all know, a lot of that is being slowly replaced by LED solutions, right? LED lighting. LEDs are light emitting diodes, which you all probably know. But what some of us might not know is that these are power electronics driven systems, right? So you can imagine a 60 watt or 100 watt bulb, and you can see this picture on the bottom left here. This bulb here consumes only 2.5 watts instead of 60 watts or 100 watts. So that's a substantial reduction in power being consumed by our lighting needs. So if you can expand that to a whole city like Chennai, right? If you can imagine all of the lighting in the city replaced by LED lighting, and the consumption of power just for lighting needs, it goes down tremendously, right? So you can see, instead of it being I think this replaces a 80 watts bulb, you have only 2.5 watts that is needed here. So highly efficient, but the key thing to keep in mind here, it is power electronics driven, right? And this is what it looks like. This is just some representative material here. So you can see here, these are the LED lamps being driven by this chip. So you have on the input side, you have AC power coming in. In India, it's 50 hertz to 30 volts. 230 to 20 volts. In the grid that we have here, it is 60 hertz, 120 is typically what we receive. So once that comes in, we use rectifiers to create a DC voltage, right? So from AC, you go to DC. And then you have these converters called DC-DC boost converters to drive currents through the LED lamps, LEDs, to create light, right? And we can take a closer look at some of these converters in the upcoming meetings, depending on the availability of time. But the thing to keep in mind is that using these controllers for DC-DC boost converters is how we drive currents through the LEDs. You can see these LEDs drawn here. That's how power is being supplied to the LEDs, right? So it's a power electronics based solution. So if you take a bulb like this, right? So in the past, this would have been a tungsten filament lamp. The filament comes in and it's got some loops, and those loops are directly applied to the 230 volts that you get from the power grid, and that burns, right? Literally burns and generates heat and light, right? This guy, on the other hand, you apply the same AC voltage, and inside of it, there is a lot of miniaturization happening. This picture is a good picture. So in this little cylinder portion is where you have all the rectification happening, the control happens there, and the driving of the current through the LEDs also happens here. Because of this, it's a very, very highly efficient system. If you have an incandescent bulb in your house and it's been burning for, let's say, 15-20 minutes, you won't be able to touch it, because by its very nature, it produces light by producing heat, right? So that's how a tungsten filament lamp works. But here the heat is byproduct. So if this lamp here, down here, even if it is 50% efficient, and it's not, it's much more efficient. Even if it is 50% efficient, you only have, 1.25 watts of heat producing from that bulb. So you can feel that it is a very cool running device as well, right? So that's about the lighting applications. Do the students have any questions at this point? Okay, very good. And Kumar Guru, in that case, I think this might be a good point to pause for this meeting, and we can meet again next week on Tuesday. Is that okay?
Yeah, sounds good. I'll stop recording.
Okay, thank you.